We'll proceed in the primitive calculus and we have calculated derivative of sin x. We will see how hierarchy works. Primitive calculus, you are everything. Everything in a sense that if someone understands primitive calculus, then only he can proceed in artificial intelligence, machine learning, these kind of scenario where the real life very complex multivariable calculus is required. So primitive calculus, what we have seen is that the addition, if I have collection rate, from collection rate, if I want to calculate the net collection, then one of the way that is very non-trivial, I would say, that no one thinks about it, that we can do addition based upon the, we can do the addition based upon the area. Whatever is the rate of collection, if I represent it as algebraic equation, and then if we draw a graph and then this algebraic equation against the independent variable, if I calculate the area, then also we can calculate the net collection. Collection rate to net collection. Collection rate to net collection is also possible through the collection rate to net collection is also possible through the calculation of the area. This is what we have learned. Okay, anyway, we have calculated the area of sin x. So area of sin x, how we calculated area of sin x? How we calculated area of sin x is like, instead of drawing the graph and then calculated the area underneath it, we went other way. So we have talked that if I have a function fx, if I have a function fx, from function fx, if I do integration, if I calculate the area, function fx becomes gx. Function fx becomes gx. Integration of fx or area underneath the fx, if I calculate, then it becomes gx. If I do the derivative or division of gx, then it becomes fx. If I know gx, for which derivative is fx, it is guaranteed that integration of fx is gx. If I know integration of fx is gx, then it is guaranteed that differentiation of gx is fx. This is rate of collection, then integration brings the net collection, gx. If gx is net collection, then differentiation brings back the rate of collection. So one is velocity vector, one is distance vector, where the fx is velocity vector, gx is distance vector. Velocity vector integration brings the displacement vector. Displacement vector differentiation brings the velocity vector. Okay, so this is what we have nicely seen, done. Now, the question that started was, what is the integration of sin x? The integration of sin x is area of the sin x curve. I don't know what is the area of the sin x curve. If I don't know what is the area of the sin x curve, then how I can calculate the integration of sin x? So we talked about two things. One is either you calculate the area and get the integration of a particular algebraic function, or you subdivide the function into lower level, so that you come to a level where you know the integration. You come to a level where you know the integration, like integration of ln x, or integration of logarithmic, that is natural log ln x. Consider that I know the integration of exponential. If that is the case, then ln x equal to y. Consider, then dy by dx we want. So if ln x equal to y, then e to the power y equal to x. So e to the power y by dx, e to the power y, d e to the power y by by dx equal to dx by dx, that is 1. If that is the case, then e to the power y by dy into dy by dx equal to 1. Differentiation of e to the power y with dy is e to the power y itself. This proves that dy by dx equal to 1 by e to the power y. Earlier we wanted differentiation of e to the differentiation of log x, differentiation of log x. So log x equal to y, we considered it. So x equal to e to the power y. Now dy by dx is 1 by e to the power y, means 1 by x. So this proves that if I want differentiation of any function and I can break it into another function where I know the differentiation, then we can kind of get it. So if I want integration of sin x, similar fashion, the way we did, if I want integration of sin x, if I break the sin x into several parts, like we did for logarithmic x, we took the help of lower level exponential. Similarly, if I have any fx, if I broke into some part and then I try to take help of those, I know the derivative or integration of those, then quickly we can find. This is another way. One way is calculate the area and get the integration, or another thing is that you break into other functions for which you know the integration. Both of things is not possible in sin x. Sin x can be broken into polynomial series, but again derivative is required. So this Maclaurin series and Taylor series is not possible here. If that is the case, then what is the integration of sin x? Let's consider that I have integration of sin x is fx is gx. Let's consider gx. Consider the integration of sin x is sin x. Let's consider the next talk about differentiation of sin x. Through first principle, we saw the differentiation of sin x, that is d sin x by dx equal to cos x sin delta x by divided by delta x, where we are not happy that it is 1 when delta x tends to 0. Then we went through trigonometric way. In trigonometric way, we have now, okay, so okay, so in trigonometric way, okay, so in trigonometric way, we consider one circle. In trigonometric way, we consider one circle. So in circle, okay, we consider this as x-axis. This is y-axis. This, then there is one radius that is on x-axis making angle 0. Then this radius is moving and it is making 90 degree, then pi degree, then 3 pi by 2, and then 2 pi. So okay, now there is another radius that is going on from x-axis and it is making angle theta. This is what we saw. Consider this point as P, and at point P we draw a straight line, vertical line. Now from P I drew, this is angle theta. I went ahead and added angle d theta. So this point is Q. From Q, draw a horizontal line, vertical line, horizontal line. Now, if this is the vertical line, then it forms a triangle here. This is vertical line, it forms a triangle here. And if this is vertical line, this is a horizontal line, then it forms a triangle here also. P point, and Q point. If I connect, then it becomes a straight line. Straight line and vertical and horizontal, it forms one triangle here also. One triangle here, one triangle here. Later we saw that if this angle is theta, if this angle is theta and this point is P and this arc, this point is Q. If this is theta, if then this point is P, and if I draw arc of angle theta, then again added angle delta theta. This point is Q, this point is P. Then if this point is Q and this point is P, then we can clearly see there is one triangle here, where arc is the third line. From P to Q, if I draw a line, then that becomes a full-fledged right angle triangle, where this angle is right angle. Then this line is perpendicular to the radius. Okay, this also we will prove it. So this angle is theta. If this angle is theta and this is the base, so base is delta y. This is what we saw. So at the beginning, this is our proof. It's not available anywhere. So at the beginning, so when it is at angle theta, then vertical is y. Then it moved delta theta, then in vertical there is a delta y difference. So if I take top triangle, then it is like this. If top triangle is like this, then it makes a kind of, this arc is the third side. This angle is theta, but if theta, then cos theta is base. This is the base. Base is delta y by the arc. That is the hypotenuse. So arc cannot be a hypotenuse. So the line connecting P and Q, if we draw the line, that line we consider it as same as arc. The line that we consider as same as arc, because arc is very small. If arc is very small, d delta theta, if there is an arc between P and Q, for this arc the angle is delta theta. It is so small that line connecting P and Q is equal to this arc. I don't like this personally, but let's consider it. Then in that case, the hypotenuse is nothing but radius is a, then a delta theta. So cos theta is base, that is delta y by a delta theta. So cos theta equal to delta y by a delta theta. If delta theta tends to 0, then cos theta equal to dy by a d theta. Now earlier, if you remember, the sine theta, this theta, the sine theta, this theta, that is y by hypotenuse. So hypotenuse is a square root of x square plus y square. That is, in polar coordinate, it is always constant. Can you see this? You move whatever angle, this hypotenuse is always constant. What is changing is height is changing and base is changing. If that is the case, then if this is angle theta, then sine theta is y by a. A is constant. So sine theta equal to y by a, d sine theta by d theta equal to 1 by a outside dy by d theta. Now we know that cos theta equal to dy by delta d theta, then dy by d theta equal to a cos theta. Substitute it, then d sine theta by d theta becomes cos theta. Now question arises is, what is the derivation of sine theta? Then answer is cos theta. We started with what is integration of sine theta. Integration of sine theta, if it is fx, then integration of sine theta is gx. Okay, if gx is sine theta, then derivation is cos x. Then certainly integration of sine theta sine x is not sine x, because sine x derivative is cos x. So what is the integration of cos x? Then sine x. What is the derivation of cos x? Let's calculate. Now this is x-axis, this is theta degree. If this is theta degree, then if this is theta degree, then this is x. Can we see? If this is theta, then this is theta angle, then this is x. Then cos theta is x by hypotenuse, x by a. If I move delta theta like this, then I have another height, but we are not interested in the height. So earlier the base was x. If I move little bit up, then base is x minus delta x. There is a decrement in delta x, x minus delta x. Now, if this is the case, then if this was the earlier x, if I move, then there will be top triangle again. And now this side is delta x and there is an angle, and you can proceed on the way did in the sin x. But a clever person, how we proceed in the differentiation integration is that if you have the most basic one, then you can proceed from it. So the derivation of sin x is cos x. 1 minus sin square x square root is cos x. So derivation of cos x, because we know polynomial derivation. The derivation of x to the power n is n x to the power n minus 1. So if that is the case, then the derivation of cos x equal to d cos x by dx equal to d 1 minus sin square x to the power 1 by 2 by dx. If that is the case, then it will come as 1 by 2, 1 by 2, 1 by 2, 1 minus sin square x to the power minus 1 by 2 into minus 2 differentiation of again minus sin square x, that will come as minus 2 cos x. 2 cut down and it become minus cos x divided by square root of 1 minus sin square x. I believe I am right. So derivation of cos x is nothing but a square root of 1 minus, what is derivation of sin square x? Derivation of sin square x is 2 sin x cos x. I am sorry. So this proves that it is the numerator is minus sin x cos x divided by square root of 1 minus sin square x. 1 minus sin square x is again back to cos x. Cos x gone, and derivation of the cos x is minus sin x. Can someone say it? What is the derivation of cos x? Derivation of cos x is minus sin x. This is how we can proceed in the, this is how calculus. One is why calculus, because we need to calculate the collection through area. That's why calculus came into the picture. How calculus. Once you know polynomial, then on top of it you can get it the sinusoidal. Basic sinusoidal we calculated as basic sinusoidal we calculated. Okay, so basic sinusoidal we calculated as y by a, the sin x equal to sin theta equal to y, sin theta equal to y by sin theta equal to y by a, and there we did d sin theta by d theta equal to 1 by a dy by d theta. Okay, so or if I go with the chain rule, then dy by dy into dy by d theta, and then later on we proceeded. So this is more or less polynomial we are seeing, that we know. Now here also, if I am calculating the derivation of cos x, then I started with a square root of 1 minus sin square x, 1 minus sin square x to the power 1 by 2. Then I differentiated with 1 minus sin square x, then again with the chain rule, then differentiation of 1 minus sin square x with the sin x. Again, differentiation of sin x with the x. So everywhere we are using polynomial equation. So since we know polynomial, since we know derivation of sin x, this is how we need to proceed upon. What is the derivation of derivation of sin cos x is minus sin x. Derivation of cos x is minus sin x. This proves that integration of sin x is minus cos x. So we got the result. What is next? What is the derivation of tan x? Tan x equal to sin x by cos x. Sin x by cos x. Now I know derivation of sin x. I know derivation of cos x. So let's go by chain rule. So actually we are trying to calculate derivation of sin x into cos to the power minus 1. So sin x and then minus cos to the power minus 2 and minus sin x. Differentiation of cos x is minus sin x. So sin x minus cos to the power minus 2 minus sin x, minus gone, and then we have sin square x cos square x plus chain rule plus cos to the power minus 1 and differentiation of cos x by sin x back cos x. So cos x and cos to the power minus 1 is 1. So now we have sin square x cos square x plus 1. That is the kind of derivative of tan x. Let's divide it by, okay, so cos square sin square x into cos square x plus 1. So cos square x means this is the derivative. So what we can do, one sec. So cos sin, I believe it's all right. So what is now, initial was sin x by cos x. So we differentiated, keeping the sin x, we differentiated 1 by cos x. So 1 by cos x is minus 1 by cos square x minus 1 by cos square x, and then minus 1 by cos square x, and then I think we did a mistake. Let's try again. What is differentiation of tan x? Tan x equal to sin x by cos x. Then go by chain rule, that is sin x into cos to the power minus 1. So sin x into minus 1 cos to the power minus 2. Again derivative of cos x, that is minus sin x. So that become minus plus, and it becomes sin square x by cos square x plus 1, that we have seen. So differentiation of tan x is sin square x by cos square x plus 1. If that is the case, then it becomes sin square x plus cos square x divided by cos square x. So this becomes sec square x. So differentiation of tan x is sec square x. Can you see that we are using polynomial differentiation and we are using differentiation of sin x and cos x? This is the way we have to proceed, level up, 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 up. So this is the story of how calculus. Why calculus? How calculus? Anyway, this is the one proof we did for the sin x, where we use the polar coordinate system. So in polar coordinate system, we rotated this radius in a polar way. So if I am rotating, this radius is constant, where height and base is keep on changing with the angle theta. This is what we have seen. Now if this is theta, if this is the height, if I move delta theta, then along, if this is P, earlier P, then this is P, then we move to Q. At P, let's draw a vertical line that we have done. If this is Y, then this is delta Y. If this is delta Y, We are not going in a polar coordinate system. What we are trying is that if this is P, this is X, let X be constant, not the hypotenuse be constant. In polar, hypotenuse is constant. Let X be constant. If X is constant, if this is theta, this is Y, if we proceed delta Y, delta theta, then go along the Y. Delta Y, Y, X remains constant. If that is the case, then d sine theta by d theta is sine theta is y by square root of x square plus y square, where x is constant, not x square plus y square, square root is constant. X is constant. If that case, the d sine theta by d theta equal to d y by square root of x square plus y square by d theta, that will come as dy by square root of x square plus y square square root by dx by dy into dy by d theta, where x is constant. If that is the case, then at the end it will come as minus x square. If I differentiate y by square root of x square plus y square by dy. So if I go with by chain rule, then it will become y into, then y into minus 1 by 2 minus 1 by 2 and then 2y. So it will become minus y square divided by x plus y, x square plus y square to the power 3 by 2 plus 1 by square root of x square plus y square. If that is the case, then this becomes x square by x square plus y square by power 3 by 2 into dy by dx. If that is the case, d sine theta by d theta equal to x square by square root of x square by x square plus y square to the power 3 by 2 into dy by d theta. Now someone has to get x square by x square plus y square to the power 3 by 2. If someone get dy by d theta equal to x square equal to, what we want is, we want x by square root of x square plus y square, that is cos theta. So d sine theta by d theta equal to x square by x square plus y square to the power 3 by 2 into dy by d theta. If I prove dy by d theta equal to x square plus y square divided by x, then we can solve it. So through this way only. Now next limitation comes is that we gave a hypothesis that if this is the if this is the, in the first proof, the proof what we did, if this is the angle theta, if this is the angle theta, if this is y, then sine theta is y by hypotenuse. Then at this moment when this is an arc, at this moment when this is an arc, at any moment this radius is perpendicular to the arc. Radius is perpendicular to the arc. Radius perpendicular to the arc. Radius perpendicular to the arc. If I prove it, then what consideration we had taken? We took that the delta theta arc we took as same as if I draw a straight line connecting these 2 points. And we said that arc length is same to this line. That is not a concern. Concern we have already talked. Concern is that this angle, if we take the top circle, if we take the top circle, what we had done in the proof of d sine theta by d theta, if they take top circle, then this angle we considered as theta only. We consider theta because this angle theta is same as this angle. This is what we took. This is consideration is only when this arc, the line we took along the arc, that is perpendicular to this line. This proves that if I prove this arc is perpendicular to the radius everywhere, then this angle is theta. If this angle is theta, then more or less we have proved it. So how we can prove that in any circle the radius crosses the arc at a point where arc and radius are perpendicular to each other? No way we can prove it. So we started a discussion that if it is a circle, then equation of circle is x square plus y square equal to a square. x square plus y square equal to a square. If that is the case, then y equal to square root of a square minus x square. If that is the case, then fx equal to y means fx equal to square root of a square minus x square. If that is the case, then dy by dx, that is partial derivative along x-axis. So dy by dx is nothing but differentiation of a square root of a square minus x square. That is 1 by 2, then a square minus x square to the power minus 1 by 2 minus 2x. 2 gone, then it is minus x divided by square root of a square minus x square. So dy by dx is minus x divided by square root of a square minus x square I. Because it is a gradient vector along x-axis, we did partial derivative along x-axis. This is another story that we don't have anything else to do also. Only thing we can do is only partial derivative in the 2D is along the x-axis. So if I have a circle, then partial derivative along x-axis is minus x divided by square root of x square a square minus x square. When x is a, at point, if this is x-axis at point a comma 0, if x is a, then it becomes minus a divided by 0, means infinity. So the gradient line, when x is a0, when y is 0, then it is completely high force along the x-axis. High force along the x-axis. This we have seen. Now we have x square plus y square equal to a square. Let's consider x square equal to a square minus y square. What is dx by dy? What is dx by dy? Dx by dy. So then dx by dy is again minus y divided by square root of a square minus y square. Minus y divided by square root of a square minus y square. When dx by dy is 0, when y equal to 0. If y equal to 0, then dx by dy is 0. Where is, now let's go back to the circle again. What we try to do is that we differentiated along y-axis, not along x-axis. If that is the case, if dx by dy is 0, means at y equal to 0, means at y equal to 0, at y equal to 0, there is no slope along the circle. This much we know. There is no rate of change. If there is no rate of change, at that moment it is parallel to the y-axis. This proves that if this is the circle, if this is x-axis, or we can say y equal to 0 axis, then at this point y equal to 0, at this moment, it is perpendicular, it is parallel to the y. If this is y-axis, at this moment the point is parallel to the y-axis, because dx by dy equal to 0. If we saw that the gradient vector dy by dx at x equal to a comma 0 is along x-axis, and at same point, the curve, at this point it is parallel to the y-axis. So this is the radius and this point is parallel to the y-axis. This proves that the angle between radius and curve, at least at on x-axis where it intersects, there it is 90 degrees. If that is the case, we can consider that radius and curve everywhere it is 90 degrees. This proof is not available anywhere else. It is our proof. So how you can prove that radius in a circle is perpendicular to the curve, the arc? This is the proof that first you calculate the radius. So if I calculated dy by dx, and that is nothing but gradient line, when x is a comma 0, then it is straightforward x-axis, and then at that point we calculate dx by dy, set it to 0, and see at that moment what is the slope. There is no slope because dx by dy is 0. At that moment, that point, if I put a line, that point, because every moment there is a slope. At that point there is no slope. At that point it is parallel to the y-axis, that is x-axis itself, y equal to 0. Means at that point radius, that is x-axis, and the curve, they are perpendicular to the each other. Okay, so this is the proof that curve and radius are perpendicular to the each other. We will proceed on it. So we will calculate the curve and radius are perpendicular to each other in many other fashion also. So this is, we tried with the gradient curve in 1D. 1D in the sense only I vector I have the gradient curve. We will proceed in I have gradient curve in the 2D, and then gradient curve in polar coordinate system. Then we will see gradient curve in 2D, but where we have in a contour fashion, that is 3D. Then full-fledged 3D gradient curve. Then vector analysis, parametric vector, velocity vector, vector field. Then we will move into much awaited topic, that is curl and flux. That is something that everyone would be interested. But those are how calculate. One by one, step by step, we are proceeding. But I can give you, like, if I have a circle, then what is the vector? If this is x-axis, if this is y-axis, if I have any point P, then what is point P? Consider the point P is x comma y. What is the position vector for point P? That is x comma y. The position vector of point P is xi plus yj. That is the, we can consider at radial vector, position vector. So if I have this as center and this as radius, then any point P is xi plus yj. Y equal to square root of a square minus x square. This is xi plus square root of a square minus a square root of a square minus x square j. If that is the case, then we can consider this as displacement vector. I had a function fx, and if I do integration, then it becomes gx. Gx is net collection, displacement, whereas this function is velocity function. So if I have displacement, quickly I can think that it is an integration of something. If I have derivative also, if I have rate of collection, then it is differentiation of collection. We can think in this fashion. So if I have a displacement vector, that is xi plus square root of a square minus x square j, then this is displacement vector. Then what is the velocity vector? If I do differentiation, I can get the velocity vector. We will see it. So now you can get the velocity vector. If you have two vectors, then if this is position vector, displacement vector, if I get velocity vector somewhere, and if I do dot product, if it is 0, then certainly they are perpendicular to each other. Then where is the velocity vector? That we have to find. Then we can say that again curve is perpendicular to the radius. That we will